Hi, welcome back. Let's continue our discussion of the small data global Wellposedness properties of the semi-linear wave and Klein-Gordon equations. And just to recap where we left off, last time we were able to establish a sufficient condition on which this row mapping, right? This will be what we want to try to prove is a contraction mapping. This row mapping from a putative solution, capital phi, to a a refined gas. This particular mapping row, we have shown that it can be well defined, provided if we have the energy flux where of the k-fold L derivative of the input, right, through every single hyperboloid is actually bounded. If we have this uniform boundedness property, then we can actually make sense of the row mapping. So we're going to try to upgrade this and actually get this to be a contraction mapping. So we need to have this mapping to be from some function space to itself, and then this is actually contraction mapping. And so the next thing to do then is to define what are the function spaces that we need to use in this argument. So I'm going to first show you what they are, and then we're going to explain a little bit their use later on. So for convenience, I'm going to introduce a shorthand notation, okay, just so that I don't write so many L's. So if I write L with an upper index in bracket, an integer k, a positive integer k, a non-negative integer k, this means a string of k L operators chained together. So it'd be L for Li for some Li1 for some I1, Li2 for some Li2. Remember I1, I2, I2, Ik. These are going to be indices ranging from 1 to d, being the number of spatial dimensions, right? We remember that we have d Lorentz boost operators, and each one of them corresponds to one of the cardinal directions. And so we have the what we're trying to do is we're going to chain together some k number of them with essentially arbitrary I1 through Ik. Okay, so this is just sort of a very shorthand notation for because we had basically just because even though we defined these weighted subgroup spaces before, right, which incorporates these L derivatives, we're going to look at integrals of L, this string of k L operators acting on my solution. I'll be looking at these L phis integrated over not necessarily hyperboloids for some parts of this argument, and so it's convenient to just introduce these operators. Okay, good. So the two main function spaces will be defined is the function space capital E to the power k and then capital script E to the power k. Okay, so what is capital E to the power k? Capital E to the power k is the energy flux space corresponding to up to k derivatives in the L operator using the L operators, and this will be corresponding to the energy flux through a constant t slice. So let's read through the definition here. So forget about supremum and outside for a moment. Look inside parentheses. In that parentheses, we're summing from j equal to 0 to k. So we're looking at the function phi with no L derivatives acting on it. The function phi with 1, 2, 3, all the way up to k different L derivatives. Now here the sum here is actually a schematic sum, basically because implicitly I'm summing over all possible. So when I say I'm summing over L to the power bracket j, I'm summing over all possible strings of up to j L operators. So combinatorially there's going to be very, very many of these objects. Okay, but I'm just going to collapse everything in this summation notation here. Okay, so I'm summing over all possible derivatives up to k, starting from 0. And for each fixed kind of derivative, what I'm doing is I'm looking at what? I'm looking at the total derivatives of this L phi, right, measured in L2. And this total derivative here means that both time derivative and space derivative. Okay, so let me just choose my pen, make sure that I have the right pen. So this is both d by dt and gradient. They both show up in this partial over here. Okay, and so in other words, right, this is the kinetic energy part of the energy density or energy flux through the constant t slice. Okay, and the second term here would be the mass term, the L2 squared, right? This with a mass over included here. This is a mass, right? So this is the mass term. So in other words, for a fixed J, right, this term here is nothing more than energy flux. Right, so this is the energy, so fixed J, this is the energy flux through THROUGA through T equal to constant. Okay, this is what it is. And I'm summing over all possible derivatives of phi by these L operators up to kth order. Okay, so I'm adding all this up. And this is my space Ek. Okay. And then, oh right, by the way, so this is, so inside here, this is an L2, these are L2 taken on the constant T slice, right? So I'm going to take the supremum over all T bigger than or equal to. Remember, we're only solving the equation in the domain T bigger than or equal to 2. So I'm taking over supremum over all times of the energy flux through the corresponding level set of time, okay? And this is capital EK. So capital E here just stands for energy. It's energy flux through the constant T slices. Okay, now how about script E? Well, script E, we're going to take the same convention as we did before, where the script version is the integral on the hyperboloid. So now script E is going to be is going to correspond to the energy flux of the L operators acting on phi through the hyperboloid. Okay, and so this formula here, it should be somewhat familiar to what we have already seen earlier when we talked about the energy, the hyperboloidal energy estimates. So here we have that again summing from J equal to 0 to K, so up to the kth order L derivatives, and we see that in this formula here, right, we have the time derivative part showing up here, right, which comes with a tau to the d weight as we expect. Okay, so this will be the Lj derivative acting on phi. It's time derivative of that, integrated along the hyperboloid in the L2 minus 1 weighted norm, okay, and multiplied by tau to the power d. And here we have the spatial derivative part, right? And because we're looking at spatial derivatives, we're looking at one more derivative, right? We have previously Lj, and then we're going to add another L to it. And the difference here is that we have d minus 2 in the tau weight, and we're still evaluating the same space. And when we're looking at Klein-Gordon equation, there's also going to be a mass term. The mass term has a mass here. It has a better weight in T. It has a different weight in the weighted integral, but you have one fewer derivative here. I have Lj. Okay, so this is precisely the energy flux of up to the kth order L derivatives of the function phi. Okay, so here we should think about phi as functions, right? So all these functions here, phi you should think of as function defined on the say t bigger than equal to 2 cross RD. Okay, this is what we're going to be doing. All right, good. Now, so this is 2R. Okay, good. So these are our function spaces. So now let's talk a little bit about what we can control using these function spaces. And one very important part, sort of algebraically, computationally important statement here is our commutator estimates. What do I mean by that? Sort of the main issue here is that because we're looking at the nonlinearities, right? The nonlinearities are of the form f of phi d phi, and in order to control the higher order energies of rho phi, right? So if you're given phi, remember we map to rho of phi, and we know that phi, we want phi to belong to want phi to belong to Ek. This is in Ek and script Ek, right? So we want to prove that rho of phi is also in Ek and script Ek, right? In order to guarantee that we have a self map before we do a contraction mapping. And if we want to do that, right, what we're going to end up is having to evaluate L derivatives of rho, L derivatives of rho phi, right? L derivative of rho phi, and then measure this in Ek and script Ek. Right, so we're measuring in these integral norms. So in order to do that, right, we're going to take L derivative. So to do so, what we're going to do is we're going to look at the formula for rho phi, which is generated by what? This is going to be generated by precisely what we had before, right? We had rho phi being the homogeneous part, right? The homogeneous part of the solution coming from initial data, plus the inhomogeneous part coming from the input capital phi. And this will require us to, when we're evaluating the weighted, the L-derived norm for this will require us to take the L-derived, taking the L operator and hitting it on nonlinearity F. Okay? So this means that we're going to hit L hitting on F, and therefore we need to think about how does L interact with partial differentiation, because F itself depends on partial derivatives of phi. Okay, so we want to think about how does L interact with the partial derivative, and to understand this, we're going to use commutator estimates. So I'll come back to why such estimates are useful in the end of this discussion, but let's just first observe the following. We know what L are. Remember that Li is defined to be, this is t d by dxi plus xi d by dt. Okay? So using this and plugging it into the expression, we see the commutator between partial t and Li is exactly partial xi, and commutator of partial xi and Lj is equal to delta ij, so it vanishes if I and j are different, but if I and j are the same, it gives you d by dt. Okay? So using this tells us that if you have a string of L operators acting on delta, acting on some partial differentiation, either by partial d by dt or d by dxi, right? I can move the differentiation all the way from all the way in the right to all the way to the left. However, what we're going to pay is we're going to be paying by instead of the right hand side, instead of being exactly KL derivatives, I have to worry about a situation where it might be some number of L derivatives which is less than or equal to K. So it's a schematic expression here. There are some implicit coefficients hidden in the summation notation, but this is schematic notation. Basically what it's saying is that I can move delta from all the way in to all the way out and vice versa by adding to it lower order L derivatives. Okay, so I'm just sort of, and this can be proven by induction, but I'm just going to give you an example of what it looks like, and then you'll understand what this looked like in sort of, you can sort of figure out how to do the induction argument yourself. Okay, so let's do an example. So we start with L1, L2 partial t. All right, so this would be the Lorentz boost in the x1 direction acting on the Lorentz boost in the x2 direction acting on partial t as an operator. So I want to sort of commute partial t all the way to the left. So what do? So first, I'm going to have to swap partial t and L2, right? The first step, I'm going to swap partial t and L2. And if I do that, I'm going to get the thing on the right-hand side, L1 partial t L2, and then minus L1 the commutator, right? Remember the commutator partial t L2 really is just by definition partial t L2 minus L2 partial t, right? Okay, so I'm going to put this in, and then we can use my formula upstairs that we computed about commutator partial t and L2 to replace this by d by dx2 over here. Right, so this goes to here. Now over here in the first term, however, what we can do is that we can also try to swap partial t and L1. And we're going to pick up another commutator term. And again, we're going to apply the rule we have commutator to get this into partial x1. And finally, I can try to swap these two terms to move the partial derivative all the way to front. And when I do that, I'm going to I observe that partial x2 and L1 actually commute because I and j are different. So now we have that this gives me partial x2 L1, and voila, we have an expression in the end where so we start with something with the partial all the way inside, we end up with a linear combination of terms with the partials all the way on the outside. So okay, and we can do this thing in reverse. So the claim is that whenever you have an expression where you have a string of L's and some partials, we can up to some lower order term by sort of, we can replace it by a linear combination of terms of lower order or of the same order and lower order, and by moving either all the partials all the way in or all the way out. Okay, so that's sort of the claim. And this is what the commutation is used for. Now, the reason that this is useful is because so up here, if we go back to the energies, right? Let's just look at the EK, the capital EK, the Roman letter EK norm. We see that the energy estimate controls what? It controls derivatives, partial L phi, right? This controls the control over here that we get here controls partial on the outside. Okay. Whereas when we take derivatives, when we take L of f, use a different color now. When we look at L acting on f by the chain rule, one of the terms would be something like f prime phi d phi, L acting on derivative phi, and we have the derivative on the inside. So what this commutator estimate is telling us is that we don't need to worry about the derivative on the inside here from the computation versus from the energy controlling with derivative on the outside, because the two are morally speaking equivalent, right? This L d phi can be replaced by terms that looks like dL phi and d phi, and both of those are controlled within the energy up top. Okay, so that's why we care about the commutator estimate. Now, let's look at energy bounds, given that we have these commutator estimates. Okay, so first we have that provided. So I included the m on the left hand side just because that the first estimate only holds in the Klein-Gordon case where m is positive. When m is 0 in the wave equation case, and the first equation, there's no control on that term coming from energies, right? Because the energy just does not include a mass term. So okay, so the energy bounds for t is bigger than or equal to 2. First, we know that just by definition, kth order L derivatives of phi integrating L2 is bounded by phi of ek. In fact, this can be any k. This k here can be switched by any j less than k. Okay. Similarly, in the wave case, if you look at Lk acting on derivative measured in L2, right? Using this commutator estimate before, we can move the derivative outside, add the sacrifice, or maybe adding some terms with lower derivatives. So if you look at k L derivatives acting on d phi measured in L2, by doing this commutation, we can replace this by the L2 of the sum of things with derivative acting on the outside, multiply acting on Lj of phi, where j is between 0 and k. Okay, and then I use triangles inequality. I can put L2 inside, and then we get this is bounded by ek. It's also squared here. Sorry, it should be a square. So we have that so this is basically sort of just again manifesting what I just said earlier, explaining why we care about the commutator estimates. Okay, so this gives an energy bound. Next, let's look at pointwise bounds. So pointwise means L infinity bounds, right? So up here, what we have here is that we have first, these are L2 bounds, and notice that we're only looking at L2 integrating space, and well, I'll explain why in a moment, but we're looking at L2 integrating space, and now we're going to look at L infinity on a constant t slice. So for the pointwise bound to hold, we're going to use a dispersive estimate, and to use dispersive estimate, we're going to use the dispersive estimate for the version where we have compact support. In particular, we're going to assume that the support of phi is contained within the set t bigger than or equal to x plus 1. Okay, so let me just draw a picture here to remind us what's going on here. So we have, this is a t, this is x, and this is t equal to 2. Okay, we're going to draw the x at t equal to 2. And t equal to 0 is down here. So this is t equal to 0. Let's say this is the origin over here. And this is the ball radius 1. This is the ball radius 1. And this is the light cone coming out from the origin. Okay? So using the finite speed of propagation, right, we expect that the solution to our nonlinear equation, because we have prescribed into data at t equal to 2 to be within the ball radius 1, we expect that the solution to be living in this part. Okay, so because of this, everything that we did before when we talk about the dispersive estimates with compact initial data still apply, right? Because when we talk about the dispersive estimates for the compact initial data case for the homogeneous linear wave and Klein-Gordon equations, what we did, right? What did we do? What we did is that we used the finite speed of propagation to guarantee that the solution is going to be within exactly the same set, and then we say, okay, because solution is going to be in this set, we can upgrade the sum of the tau factors into t factors. Okay, and so the exact same geometry argument applies here, provided we have that the energy flux through the hyperboloids are uniformly bounded. Okay, so let's go back to where we are. So we shall assume that support phi is within the set that we expect it to be supported in, and from which we can use this compact data type argument. And this tells us that we have two sets of arguments, and we're not actually going to be using an n positive one for our actual proof, because I'll discuss why it can be useful later on. But when m is positive, so in Klein-Gordon case, what we have is that the solution itself, phi, or the function itself, phi, if you take k derivatives of it using L derivatives, you measure this in L infinity, right? This is going to be bounded by 1 over t to the power d over 2, and in key here is that this decay rate, d over 2, multiplied by the phi's norm on the script E space of k plus d hat plus 1, right? Script E space, this is the hyperboloidal energy space, okay? This k here corresponds to the k that I assumed was there. And in order to estimate this object in L infinity, I have to sacrifice, using Sobolev inequality, another d over 2 derivatives. This is why I have this factor added to it. Okay, and this is precisely the global Sobolev inequality essentially that we have before. Okay, when m equal to 0, and actually this is when m bigger than equal to 0. This always works in both cases. When m bigger than equal to 0, so in a way, so the first expression is not available for the wave equation. It's only available for Klein-Gordon. But if you want to use, but for both wave and Klein-Gordon, the following version also holds, which is that the derivative of L with k factor of phi, right? This particular object measuring L infinity, and this is what we proved earlier when we proved the dispersed decay, is that this is going to be bounded by 1 over power t to the power d minus 1 over 2, multiplied by what? By phi measured in, again, the hyperboloidal energy space. K is the number derivative here, and then we have the additional derivative sacrificed for the Sobolev inequality. Okay, and basically this estimate here uses the kinetic energy part, the non-mass part of the energy, which has one higher derivative, and the previous estimate uses only the mass part. So the reason that we have the difference in power here, t to the power d half and t to the power d minus 1 over 2, is effectively due to the fact that in hyperboloidal energy, if you want to measure derivatives, you have a t to the d weight, so heavier t to the d weight, and a minus 1 weight over here. And for the mass term, you have the same d weight, but you have a 0 weight here. Okay, and it is this difference, this 0 weight versus this 1 weight over here, okay, that drives the difference in decay rates over here that you can see in the pointwise bounds. Okay, and this is something that we discussed previously. Also, when we talk about the basic dispersive estimates for the wave and the Klein-Gordon equations. All right. Okay, so these are the pointwise bounds that we're going to have. So based on these pointwise bounds, let me just talk about how we can actually use this to estimate the nonlinearity, right? Because nonlinearity, estimating nonlinearity is somehow the key concept that is going to be factoring into our strategy here. Remember, right? We want to prove the boundedness of energy flux implies the boundary energy flux for the new thing, and the energy flux for rho phi, remember, is going to be depending on the homogeneous part plus the contribution from the inhomogeneous terms, right? And the homogeneous part is only going to be based on initial data, and since we're looking at initial data we can just prescribe to have the requisite number of requisite control on initial data, and we'll be done with this. And so what's important for the boundless energy flux is to be able to control the contribution to the energy flux from the inhomogeneous terms, and this requires taking L derivatives of the nonlinearity and then seeing what happens when we try to estimate it. So let's see what happens when we look at the if we sort of act the L operators on the nonlinear object f, which depends on phi and d phi. And you should mentally remember that in the wave equation case, there's no phi term. Okay? So what you're going to do is that if you take this and just use chain rule, this is going to be represented by a sum. Okay? So in the first term of the sum, this is a pth order derivative of f, right? Okay? And so this means that when we're looking at derivative, the differentiation hits f p times. Okay? So this means that if each time the differential hits f, right, what you're going to get is by chain rule, you're going to get a L derivative, corresponding L derivative hitting on the arguments plugged into f. So this tells us that there should be total of p objects on our right hand, and exactly we have lk1, lk all the way through lkj, lkj plus 1, all the way through lkp, right? So we have p terms on the p different phis that's generated from hitting on the pth order derivative of f. Okay? And then for the chain rule to work, right, basically what's going to happen is that we're going to have k1 plus k2 plus k3 all the way to kj plus 1 all the way up to kp, right? The total number of L derivatives on the right hand side has to equal to the total number of L derivatives on the left hand side. So what's happening is what? Imagine that you have, let me just sort of very quickly do an example so you can see what's going on here. So we have, let's look at the wave equation case for simplicity, right? We have L2 acting on F, and then we have d phi, right? So this is equal to what? This is equal to some L derivative acting on the first derivative acting on this. So this gives me F prime d phi times L1 derivative acting on d phi by the chain rule. And by the product rule now, we're going to get either the L derivative acting on F itself. So this gives me two derivatives, d phi, and then I get L1 d phi, L1 d phi, plus one derivative acting on this, and I get two derivatives acting on d phi, right? And exactly this is what the sum over there is meant to accomplish, right? We can have at most k times the derivative hits on f, but p can be less than k. Okay, so in the two case, right, we have either one derivative hitting on f or two derivatives hitting on f, shown here. Now, when two derivatives hitting on f, there must be two different d phi terms generated from the arguments. And you can see here, there's two different d phi terms, and then we have each one hit on it by some number of l's. This we get L1 hitting on one, L1 hitting on other. Now, when only one derivative is used, there's only one d phi term generated, but that means that the exterior second L derivative has to hit on this L d phi to make it a 2L derivative of d phi. And so we see that every single term is the conservation of total number of L's, right? So we see that starting with 2L derivatives, in the end, we're going to have 2L derivatives. Either the 2L derivatives split up or they're joined together. And so what we're going to have here is that we're going to have P has to be less than or equal to K and has to be at least 1, because when the very first application of the process, the L derivative has to hit on F, okay? And then we're going to have that K1 plus all the way to Kp is exactly equal to capital K, and each one of the K1 to Kp is individually at least 1. You cannot have zero derivatives hitting on it, just because this is coming from the chain rule. And so we have some of these basic algebraic properties of just using the chain rule and the product rule, and you see this, and you can prove this by induction. But sort of you're a mature mathematician, you can just imagine this in your head and accept that this is true. Okay, now the key thing here is that because I know that K1 all the way added up to Kp is equal to K, right? By the pigeonhole principle, at most, sorry, this is a capital, this small t here, at most one of K1 to Kp can take up more than half of the available derivatives, right? Because they all add up to K, so at most one can be more than half. Okay, so this is sort of a very basic pigeonhole principle. So this tells us what? This tells us that we can actually schematically write Lk, so K times L derivatives acting on F, in the following way. We can write it as we can write it as some function g. I'm going to tell you what g is depends on. Some smooth function g of its argument multiplied by linearly L with up to k derivatives of phi and dphi. So this here I mean that really, so this is less than or equal to k and also bigger than or equal to 1, by the way. So this will be L phi, L squared phi all the way up to LK phi, and then L d phi, L squared d phi all the way up to LK d phi, right? These are the things that, and this depends linearly. The key thing, this is linear, this appears linearly. And what we have is that the smooth function g now, g has to be a smooth function of up to k over 2 derivatives. So basically what I'm trying to say is this. When you looking at expression above, up here, when you look at the expression I was just shown before, at most one of them can be bigger than k over 2. Okay? So if we take k1 all the way to kj, also k1 all the way to kp, and just extract the largest of them, right? All the smaller one cannot be bigger than k half. So it's at most k over 2 floor, so the rounding down of k over 2, right? So we're going to group all those terms together into g. So g is going to be something like fp of phi and d phi, right? Multiplied by some numbers of L derivatives of phi, some numbers of L derivatives of d phi, but for each of the terms, the number of L derivatives is at most k halves. At most k halves. Okay, and for this g, this is going to also depend, because it depends also on f, the p derivatives of f, right? It's also going to depend on phi and d phi itself. So this final linear term is going to have at least one L derivative, but the term in g can have 0 L derivatives. Okay, so we have a smooth function of up to k over 2 derivatives of phi and d phi by L operators. And additionally, since we know that f vanishes quadratically, right? If f vanishes quadratically at the origin, and you look at the derivative, then this tells us what? This tells us that if we take, we're going to expect that g of 0 is going to be equal to 0. Okay, this is just sort of a very simple statement. Just because f is going to be quadratically, right? Sort of that if you have a linear portion, right, the factor out linear portion, then you're going to have dependence only on a linear dependence that's left. Okay. Yeah. In other words, if g were have a non-zero value, a non-zero value, right, then this can only have come from the fact that f has a linear term, and this cannot be the case. So okay, so we have that g of 0 is equal to 0. So okay, so now we have a very nice schematic decomposition of, so remember that f is some arbitrary smooth function of phi and d phi. This is a very nice schematic decomposition of what the higher derivative of f looks like relative to the L differential operators. Okay. All right. So this lecture has gone long enough. So I'm going to take a break here, and then we're going to continue by talking about how we can estimate these derivatives of f. Specifically, how can we measure these when we try to integrate it in L2 in space?